Welcome to another episode of Breaking Math Podcast, where we unravel the mysteries of science, geometry, and technology. I'm your host, Autumn and I'm joined by my co-host, Gabriel Hesch. Today, we're embarking on a fascinating journey into the realm of molecular conformation and the revolutionary role of machine learning in this field. Our discussion will cover the latest advancements in computational chemistry, delve into innovative methodologies, and explore how they are transforming drug discovery and molecular research. So join me in this episode to unravel the journal submission Towards Equilibrium Molecular Conformation Generation with GFlowNets by Volokova et al. In Digital Discovery Journal by the Royal Society of Chemistry.
To set the stage, let's start with a fundamental concept in chemistry: molecular conformations. Molecules exist in three-dimensional space and can adopt various shapes based on the arrangement of their atoms. These shapes, or conformations, are crucial for understanding molecular behavior and predicting properties. Molecules are not static entities. They are dynamic and can change their shape due to the rotations around chemical bonds. The likelihood of a molecule being in a specific conformation depends on its formation energy and follows what's known as the Boltzmann distribution. This distribution helps us understand which conformations are more probable at a given temperature. Knowing the most probable or low-energy conformations is essential for predicting molecular properties and behaviors, which has significant implications for drug delivery and other applications.
Now let's dive into traditional methods used to explore these molecular conformations. One of the most accurate approaches is molecular dynamics simulation. This technique involves solving Newtonian equations of motion to simulate the time evolution of a system. By integrating these equations with the forces derived from the system's potential energy, molecular dynamics can provide detailed insights into how molecules move and change over time. However, while molecular dynamics offers high accuracy, it comes with a significant drawback. The process involves simulating a vast number of atomic interactions, which can be prohibitively slow, especially for large molecules or when high-throughput screening is required. Simplifications to the energy function can reduce computational costs, but at the expense of accuracy.
In contrast, cheminformatics methods offer a faster, albeit less detailed approach to conformer generation. These methods rely on experimental data, chemical rules, and heuristics to generate plausible three-dimensional structures from molecular graphs. Techniques like experimental torsion distance geometry with additional basic knowledge, or ETK-DG, implemented in tools such as RDKit and commercial software like Omega, are popular for their speed. However, they often lack the precision and generalization needed for complex studies. Enter the era of machine learning. Recent advancements in this field have introduced new methods for generating molecular conformations. Deep learning approaches such as geomol, geodiff, and torsional diffusion have shown promise, especially in handling complex molecular systems. These methods leverage large data sets to train models that can generate molecular conformations more efficiently than traditional methods.
Yet, these machine learning approaches have their limitations. Most of them focus on maximizing the likelihood of conformations within the training dataset, which doesn't always align with the goal of sampling proportionally to the Boltzmann distribution. This is where Generative Flow Networks, or GFlowNets, come into play. GFlowNets were initially introduced for amortized probabilistic interference in high-dimensional discrete spaces. Recently, they have been adapted to work with continuous or hybrid spaces, making them highly relevant for molecular conformation generation. The core idea behind GFlowNets is to sample from an unnormalized probability density, which is represented as a reward function over the sample space.
Here's a more detailed breakdown of how GFlowNets work. The process begins with a starting state and generates a sequence of updates to transition through various states until a final state or conformation is reached. This trajectory is governed by a trainable forward policy, which defines the probability of moving from one state to the next. Once a trajectory is complete, a reward function evaluates the final state, guiding the training process. GFlowNets also incorporates a backward policy, which models the probability of transitioning back to a previous state. This addition provides greater flexibility and allows GFlowNets to model a richer family of distributions over the sample space.
For molecular conformation generation, GFlowNets focus on sampling torsion angles, which are critical for defining a molecule's shape. The torsion angle is represented as a hypertorus, and GFlowNets generate trajectories through the space to explore various conformations. The reward function used is based on the molecular conformation's potential energy, which helps GFlowNets produce diverse, low-energy conformations. To define the reward function, GFlowNets use the potential energy of the molecular conformation, calculated from the sampled torsion angles. This energy is computed using an approximation of quantum mechanical density function theory, DFT. Differential energy estimators such as GFN2, XTB, and GFNFF offer varying trade-offs between accuracy and computational cost, impacting the performance of the GFlowNet.
Let's delve into some empirical results that highlight the effectiveness of GFlowNets. In initial experiments, GFlowNets were tested on molecules with just 2 torsion angles, such as alanine dipeptide, ibuprofen, and ketorolac. This setup allowed for a detailed analysis of how well GFlowNets could sample from the target distribution and compare their performance against traditional methods like Markov chain Monte Carlo or MCMC. The findings revealed that GFlowNets could accurately reproduce energy surfaces, often outperforming MCMC in some cases. The low-dimensional experiments provided valuable insights into how GFlowNets handle sampling and energy estimation, setting the stage for scaling up more complex systems.
Moving on to higher dimensional settings, GFlowNets were tested with molecules featuring up to 12 torsion angles. For this part of the study, molecules from GEOM drugs, GEOM drugs dataset were used. This data includes drug-like molecules with varying numbers of torsion angles and serves as a benchmark for evaluating conformer generation methods. In these experiments, GFlowNets were compared to several baselines, including MCMC, RD-KIT, ETKDG, and a recent approach combining ETKDG with clustering. These results showed that GFlowNets could generate conformations closely matching ground truth data and performed well in sampling from the Boltzmann distribution. This indicates that GFlowNets are capable of handling complex, high-dimensional molecular systems effectively.
Another critical aspect of this research is the choice of energy estimator. Different methods from highly accurate GFN2 XTB to faster but less precise approaches like GFNFF and Torch ANI were evaluated for their impact on performance. The results highlighted that GFlowNets, particularly when using the GFN2 XTB estimator, provided high-quality samples and demonstrated strong scalability to higher dimensions. The scalability of GFlowNets was further examined by analyzing the correlation between the